Right now, wherever you are, I want you to close your eyes for just a second. Vividly imagine a shiny silver coin flipping end over end in the air. Got it? Okay, now erase that and picture a physical cube floating right in front of you. Now watch that cube rotate exactly 90 degrees. You probably saw that pretty clearly in your head, right? Well, here's the absolutely fascinating part about what your brain just did. That mental simulation, your internal mind's eye, has absolutely zero to do with language. None at all. And honestly, this exposes a massive fundamental flaw in how our current most advanced artificial intelligence models are being trained today. Welcome to the Explainer.
You see, you and I understand that if you drop a coin, it falls. We know this because we possess physical intuition. We literally grew up observing the laws of physics, cause and effect, mass, and gravity over decades of living in the real world. But large language models, or LLMs, they're completely trapped in this weird abstraction. We feed them trillions and trillions of text tokens, but they've never actually experienced the physical world. They've only ever read our highly compressed summaries of it. So how on earth do we bridge this cognitive gap?
Well, here's our roadmap for this explainer. 1. AI's physical gap. 2. Defining world models. 3. Generative versus predictive models. 4. Real-world applications. 5. The simulation engine. And 6. The path to AGI.
Let's jump right into part 1. AI's physical gap, the token trap.
We really need to understand exactly why reading about the physical world is vastly, fundamentally different than actually experiencing it. Take a look at these two sentences. The egg cracked after being dropped versus the egg was dropped after cracking. Now, to a standard language model operating purely at a token level, these two sentences are basically identical. The words are just shuffled around a bit. But to you, me, or a physics-aware model, these represent completely different physical realities. An LLM is just predicting the next most likely token. It doesn't inherently understand that an already cracked egg behaves totally differently when dropped than a perfectly intact one. Which brings us to Section 2, Defining World Models, Building a Machine's Mind's Eye. To fix this token trap, researchers have turned to an incredible concept that essentially forces AI to learn how the physical world actually changes over time. And the history here is absolutely wild. It dates all the way back to 1943. A Scottish psychologist named Kenneth Craig proposed that the human mind has a small-scale model of reality, which lets us try out alternatives and safely figure out what to do before we ever take action. Fast forward 75 years to 2018, and researcher David Haw publishes a groundbreaking paper, appropriately titled World Models. He actually trained an AI agent to play a version of the game Doom, not by interacting with the real game, but by leveraging a small internal model to literally imagine how its actions would play out. And today, every major lab is racing to build these. NVIDIA has Cosmos, Google has Genie, Meta has JPA. It's a gold rush. So, in the strictest machine learning sense, what does a world model actually do? It basically boils down to a 3-step engine. Step 1, observe the current state of the world. Think of a single frame from a car's dash cam. Step 2, inject a hypothetical action, like turn the steering wheel left. And step 3, predict the future state of the world based on that specific action. It computes the consequences of an action before it ever actually happens. Moving right along to Section 3, generative versus predictive, two schools of thought. Now, this concept has actually created a massive technical divide in the AI industry. Everyone agrees on the input, current state plus an action. But what exactly should that predicted future state look like? Well, generative models like NVIDIA's Cosmos or Google's Genie output the future world state in a human-friendly form. They generate actual, pixel-perfect video frames. And hey, this is amazing if your end goal is human consumption, like creating video games or interactive 3D worlds. But the predictive school of thought says this is deeply inefficient. If the AI is acting autonomously, say it's a robot or a self-driving car, it doesn't need to see pretty pixels. It just needs abstract mathematical embeddings. And this brings us to a really vital concept called latent space. AI visionaries like Meta's Yann LeCun heavily champion this predictive approach. His argument is that a generative model gets completely bogged down in irrelevant pixel details. I mean, think about a road. A road is the exact same physical road during the day as it is at pitch black night. The physical laws haven't changed, but in pixel space, day and night look completely different. By computing the future in a compressed, latent space, the AI learns the fundamental laws of the world without getting distracted by the visual noise of changing light or weather. Let's see how this plays out in Section 4. Real-world applications, from dashcams to Minecraft. It's one thing to talk about latent space in theory, but how are these tech giants actually using world models right now? There are three main categories where this tech is proving to be a total game changer. First up, generating synthetic data for things like autonomous vehicles. Second, creating interactive virtual environments where humans can explore AI-generated 3D worlds. And third, model-based reinforcement learning, or MBRL, where physical robots practice tasks purely inside a simulation before they are ever deployed into the real world. Take self-driving cars, for example. Let's put this into perspective with a massive number. 365,000. Why does this matter? Well, if you're teaching an AI to play chess, the action space is incredibly small. You have an average of maybe 8 reasonable moves at any given time. But a self-driving car? If a steering wheel has 365 degrees and the brake and gas have 10 levels of severity each, you are looking at over 365,000 possible actions every split second. Plus, the driving environment is effectively infinite. We literally cannot record every possible traffic scenario in the real world. So companies use world models to dream up hyper-realistic synthetic dashcam footage to test life-threatening scenarios safely offline. Or consider this incredible milestone from a model family called Dreamer. For years, training an AI to mine a diamond in the video game Minecraft from scratch was a totally unsolved problem. It was just too complex. But researchers trained a world model by having it watch gameplay, and then let an AI agent practice inside that model's hallucinated simulation. The agent learned how to mine a diamond without ever directly interacting with the actual game first. It learned the whole thing completely within a dream state. Section 5. The Simulation Engine. Solving Sample Efficiency. The whole reason researchers are so obsessed with AI dreaming is to solve this exact problem. Sample efficiency simply means how many examples do you need to see to learn a new skill. Human sample efficiency is off the charts. We can learn a new game after just a handful of tries. Traditional AI, it usually needs tens of millions of data points to learn that exact same thing. But world model agents are rapidly closing this gap. By letting an AI practice its policy over and over inside a cheap, rapid mental simulation, just like that Minecraft agent, it needs a mere fraction of the real-world data. And hey, if you think practicing in a dream state sounds a bit like sci-fi, listen to this shocking cognitive study from 1967. Researchers took 3 groups of people to shoot basketball layups. One group physically practiced for hours on the court, and their accuracy improved by about 24%. Another group was blindfolded and only mentally visualized shooting those layups. Their improvement? 23%, almost identical. Internal mental simulation is staggeringly effective. We humans do it naturally, all the time. And now we're engineering machines to do the exact same thing. Which brings us to our final section, the path to AGI, bridging the final gap. So we've seen how world models are moving AI away from just guessing words to actually understanding physics, cause and effect, and spatial intelligence. Many researchers believe this is the definitive path to AGI, or artificial general intelligence. There's this really powerful theory from a Stanford neuroscientist pointing out that in human evolution, the entire point of the great cortical expansion 10 million years ago, the reason our brains got so much bigger and more complex, was specifically to get better and better at world modeling. We evolved from just reacting blindly to our environment to being able to simulate the future in our minds, plan ahead, and adapt. Which leaves us with this final, incredibly provocative question. If the human brain's defining feature, the very thing that makes us uniquely intelligent, is our ability to function as the ultimate world model, is engineering and artificial imagination the final missing piece of the puzzle? Have we finally found the bridge that takes AI from being a really smart text calculator to a true, reasoning, general intelligence? It's a fascinating paradigm shift, and it's happening right now. Let that sink in. Thanks for joining me on this explainer, and keep your eyes on this space, because the machines are officially starting to dream.